Hello and welcome everyone. So I'll be explaining um, Google Kickstart 2021 round A, problem B and problem A. Well, problem A was pretty easy, but let's explain problem B first. Here name is L-shaped plots. So in this problem, basically what you have to find out is you're going to be given a grid of R rows and C columns, and inside that grid you just have to find how many L shapes are there. Okay, and they have also characterized how the L shape might look like. Now here L shape is defined as an unordered pair of segments, and the main thing that here of this L shape is that the length, it's basically the general L letter that we use exactly, and the exception part is that that the two parts that when we segments each and every segments of the L shape, its length would be at least 2, and the length of the longer segment is twice the length of the shorter segment, which means let's say I have a L shape like this. If one part of that L shape is 1, 2, 3, 4, 5, let's say like 5 squares, small squares, and then if I wanna denote it as the preferred L shape here, then the other part should be either 1, 2, 3, 4, 5, which means it will be 10. There will be exactly 10 lengths, 10 parts of that on the perpendicular part. So the L is generally the L shape is basically the same as they have denoted. The exception part is the smaller length parts times 2 would be the greater length part. So that's the main exception. So we have to somehow manage and try to find out the L shape where the small part's member times 2 is equal to the perpendicular other greater part. Okay, and for this part I actually used binary search to look for. I will tell you how, but the most important thing is we have to find out how many of these L's are there inside my grid. Now that grid will consist of only two values, either 0 or 1, and we are only considering L shape of one value, so we will only consider one values of segments. And now what we have to do is we just have to find out how many L's are there. Now what I did was I tried to make each and every L, you have to make each and every L different. So in order to make it different, what I did, I tried to find out what is the point where two of the segments collide. Now this is the point where two segments collide. Now what I actually did was, okay, I'm given a grid like this. My target was to check for each and every collide position whether I can make any segments to the right or to the left, okay, combinational. For let me show you here more clearly to make it distinct. Let's say, okay, there we go. 3, 1, 2, 3, 4, 5, 6, let's say. Okay, so I know there will be some values 1 and some values 0. How do we make sure that this L is distinct and not appeared any other places? The only way that that I thought that the only way I can make sure that yes, this is the only distinct L, is to make sure if you follow the point which is um, the crossing point of the two segments. Okay, so I am actually denoting each and every one as, okay, this is my L's crossing point, and now I'm gonna be trying to make whether I can make L from this crossing point, which is there will be at most what, 8 combinations there could be. How will there be 8 combinations if I denote each and every each and every cell's one value as a crossing point of the two segments? Then there will be if I denote that point as my crossing point, then there will be, of course, there will be 8 possible combinations where the result might be L, and they will be different L. Again, to make it distinct L, I am actually focusing on the crossing point. So if I denote it as a crossing point, two segments crossing point, then I will be definitely sure that each and every L will be different. So after denoting that crossing point, I'm trying to make the L. And now for each and every crossing point, there can be at most 8 combinational L's. How is that? Let me show you. How is there 8 combinational at most? Now, let's assume that this is my crossing point. I will have some values, consecutive values, of course, consecutive values of 1 up to this. Let's assume up to this to right, up to this to left, up to some values. It could be up to some values to up, and up to some values to down. Now, if you make an observation here, you will understand that I will get one L like this, in this way. Yes, there's a possibility I can make something out of it. I can also make L something like this. Okay, so 1, 2. Similarly, 1, 2, 3, 4, 5, 6, and 7, and 8. That's it. So basically what we have to do for each and every denoting cell value 1, we will denote it as, yes, this is my tracking point of the two segments, okay, where the two segments collides. And for each and every colliding point, I'm going to try to make whether I can make the upmost consecutive ones and leftmost rightmost consecutive ones as something I can make L. So the combination could be up left, up right, right up, also up left, left up, okay, and left down, down left, okay, left right, right, not left right, down right, right down. So there will be total, there could be total at most 8 possible combination. And I hope you get that. Now the burning question is, how am I making sure quickly, efficiently, that how many L's I can make from this part? Now you might assume that, okay, I know that there are some values here, 1, 2, 3, 4, 5, 6, 7, let's say 7, let's say 8, and I have something 1, 2, 3, 4, 5, 6, let's say 7, okay, 7, here's 7. Let's assume these lines, small lines, as one of my cells, and I'm dealing with this L shape. So 1, 2, 3, 4, 5, 6, 7, 1, 2, 3, 4, 5, 6, 7, 8. So there are 8 cells consecutive of 1s, let's assume, and this is the colliding point. So total of 9 cells consecutive 1, and total of let's say, okay, let's delete this 2. 1, 2, 3, 4, 5, 6. Okay. 1 2 3 4 1 2 3 4 5. Okay, 1 2 3 4 5. Okay, let's say 5, and here the part is 9. Okay, now if I if I try to find out my L's for the combination of down and right, not right down, down and right. Okay, so for down and right, okay, then I will assume that this is my first segment and this is my second segment, which is the bigger one. So down segments, I know for down right combination I can make an L shape, something like this. Here I've got 2 portion and 1 2 and 3 4, so this could be one possible. Okay, from the down part I can get 2 cells here, and from the rightmost part I can get 4 cells, which is making 1 L. Also I can make 1 2 3 1 2 3 3 times 2 means 6. 1 2 3 4 5 6, so this could also be another L. Similarly, there could be some possible number of L's, but how we're making sure that we're making it efficiently in trying to find out this number of L's efficiently, how we're making that, how we are making sure about it. The only way and efficiently that I thought that it would be possible is to use binary search. Now, how am I making sure that it's going to be possible? It's to make binary to apply binary search here. Now, for let's assume so let's explain how we're going to be dealing with the binary search approach to find out this L shape. Now, what I talked about is here the down part had 1 2 3 4 5 cells. Down part had 5 cells, and the rightmost part had 9 cells. Now we're gonna be so far we're dealing with down right. Okay, down right had 5 cells, and down part had 5 cells of L, and the right part had 9 cells. So I'll be dealing, this is my source portion and this is my destination. What I'm trying to make sure is, I know that 5 times 2 is 10, which is greater than 9. But I also know that 4 times 2 is 8, which is less than 9. Now, if you could have a slight observation, you will understand that yes, I can simply do the lower bound. I could try to find out the lower bound. This is exactly the lower bound, and finding out that lower bound inside the combination, there would be something like this: the meet times 2, whether the meet times 2 is less than or equal to my source part. So if I could somehow using binary search find the greatest position, the greatest value which is less than or equal to my destination value, if I could somehow make sure that, I will know that this is my answer. This is my highest bit of L shape that I can get. So if I could know the highest number, the greatest number, times 2 less than or equal to the bigger segments or the other segments, then I will know that the only segment that I have to delete is the segment 1, because segment 1 is not part of my L. Now what do I have to do? When I will try to find out that, after finding out, just subtract it by 1. I will just subtract it by 1 to make sure that everything goes on the right track, because I know one cell 1 is not going to improve my result. Okay, so I hope you get this part. Now let me take you to the code part, and for the consecutive ones part, we're actually dealing with some prefix and suffix stuff, and so let's take you to the code part. I hope you understand. Let's see. This is the binary search part where I'm trying to find out, and okay, so taking the test case, and I'm actually declaring apart from my adjacent the whole grid, apart from the whole grid, I have 4 other grids of leftmost. These values, these 4 values, are just calculating the consecutive ones for each and every one. So for each and every colliding point, I'm making sure what are the maximum consecutive left, maximum consecutive right, up and down. So and taking those values, those values, and then initializing the other four positions as equal to 0. After that, for each and every side, left, right, up and down, I'm making sure I'm trying to find out for each and every sequence, for each and every cell where there is 1, what is the rightmost, what is the leftmost consecutive ones available, because I have to find L consisting of only values which denote as 1. So exactly, this is for the leftmost part, this is the right part. For each and every elements, each and every cell's right part, left part, up part, and the down part. After that, my main task is here. So the fun part is here. Inside, then I will try to traverse the whole grid. Inside that whole grid, whenever I find a value equal to 1, a cell's value equal to 1, yes, I will denote it as my colliding value of 2 segments of L. Just assuming that, I will try to find out whether I can make maximum out of L shape out of this. So, and this is the upright part, as I told you before, the upright part, also making sure that each and every consecutive ones of each and every part is greater than or equal to 2, because they have said that segments must have length at least 2. So upright, inside that upright meaning upright type of length. So upright type of length will have also vice versa type, which is right up. So both of them will be considered, and this solve function is basically find out the value that we actually told you before, using binary search. Here binary search is making sure the maximum value times 2, which is less than or equal to my destination value. So if I could somehow make that value for sure, then I know my answer is minus that value minus 1. I hope you get that. And after that, here up left, okay, up right, up left, and then down right, down left. Inside each and every this part, I'm also considering the vice versa part also. For up left, I'm also considering the left up. After gaining that value, the answer will be plus equal to minus 1. Okay, temp minus 1. And this temp value is giving the greatest number, which is greatest number times 2, which is less than or equal to the destination value. I hope you get that here. And finally, outputting the answer of how many L shapes that we got from this grid. And let's talk about problem A, which was goodness string. K, goodness string. This problem was pretty easy. I actually messed up. I totally messed up for some reason. I don't know why, but finally I did try to accept that solution, and it got accepted. So basically what you have to do is they've said that just find the minimum number of operations to make the string as string's goodness score equal to K. So I hope you read the total statements so that you know everything that they have said. I'm just describing the solution here. The solution is just try to find out how many steps that I already have, the positive score that I already have. I'll count those values, and which is they have said that the goodness will be dependent on um, if I denote a string like this. If I denote a string like this, let's say A, B, C, C, B, D, I'm only considering like palindromic transition type. So comparing this to this value to this, but the first to last, and just increasing and decreasing on both of the sides, and comparing. So the good portion will define this if they are not equal. Okay. So what we're going to be trying to do is trying to find out how many of these values are here, where the first and the last one, the prefix character and the suffix position character, are not equal, and then we will see that whichever one is if that value is already less than or equal to k, it's less than k, then the answer will be k minus that value, k minus that goodness value, because I need at least k minus that much of count k minus count, that much of temporary value to make it k goodness string. If it's greater than k, then I know that yes, I have to make not good, that extra not good part, okay, which is going to be c and t minus k. If c and t is greater than k, then c and t minus k, because that part of position that I have to change to make it not good. So if I could transform that part to not good, then the whole string will be k good, because that was already greater than k good. So goodness part defines by that, and that's how you will do. So that's exactly what I did here, taking the test case, taking the strings, and comparing it like we try to find out in palindrome, similarly like that, and just the ABS, the absolute value of k minus c and t. That's going to be the final answer, and then clearing the string. So that's it, I guess. I hope I made you understand. Till next time, goodbye.